Today I've got a lemma that I want to prove. And that is that 1 plus n squared over 2 factorial plus n cubed over 3 factorial, and so on up to n to the 2n divided by 2n factorial is at least 1 minus 1 over n times e to the n. And the way I'm going to be proving this is using some results from probability, which is quite cool. Before we dive into a proof, a couple of comments about this. Firstly, the left-hand side is just the first 2n plus 1 terms of the expansion of e to the n, the Taylor expansion. So in particular, if n is large, this left-hand side is very close to e to the n. But the same is true of the right-hand side. If n is very large, the right-hand side here is 1 minus 1 over a large number, so that's approximately 1 times e to the n, so it's going to be just slightly smaller than e to the n. So both the left side and the right side are both slightly smaller than e to the n, but the left side is supposedly slightly bigger. And I guess another second observation is that once we prove this lemma, in fact, we can turn this into a strict inequality. The reason being because this left-hand side here is clearly a rational number, because n here is a positive integer, whereas the right-hand side is irrational because it involves that e to the n. So it would turn out that these can't be the same. So therefore, even though it's bigger than or equal to, we could actually change it to bigger than. Anyway, those are some minor points, just interesting observations. Let's dive into the proof. We're going to be using Chebyshev's inequality, which is a pretty standard result from probability, but I'll state it regardless. It says that if you have a random variable x, and it has the property that the expected value of x is some number mu, and the variance of x is sigma squared, where sigma is some positive real number, and you also choose k to be whatever positive real number you want. It then turns out that the probability that the absolute value of x minus mu, the probability of that being bigger than k times sigma is less than or equal to 1 over k squared. This is true. This is Chebyshev's inequality. I wouldn't prove this, but let's just maybe appreciate what this says. This says that if x is far away from mu, what are we defining from far away? We're just saying the distance between x and mu is at least or strictly bigger than k times sigma. We want that to, the probability of that happening is a small number, i.e. less than or equal to 1 over k squared. We're going to be using this result. So to do that, we need to choose a random variable x, and we're going to choose x to be a Poisson random variable with parameter n. And a great thing about Poisson random variables is that their expected value, or their mean, is n, and their variance is also n, or whatever this parameter is here. Great. Okay, cool. And we're going to choose a value for k. In particular, it's going to be the square root of n. And since n is a positive integer, k will be positive, so that guy's satisfied. So let's now sub all this into Chebyshev's inequality. This then tells me that the probability that the absolute value of x minus n being bigger than, k sigma, well, if k is root n, sigma squared is n, so sigma must be root n as well, so k sigma will be n. It's going to be less than or equal to 1 over k squared, which is 1 over n. Okay, cool. So this is what Chebyshev's inequality tells me. But what is this actually telling me? This is saying the probability the distance x is from n is bigger than n has a small likelihood, 1 over n. Well, what does this give us? Well, this tells us that either x is smaller than 0 or x is bigger than 2n. So the probability x is less than 0 plus the probability x is bigger than 2n is at most 1 over n. But x is a Poisson random variable, so x can't take any negative values. So that guy is just 0. So we can just focus on this. The probability x is bigger than 2n is at most 1 over n. And what's that? Well, that's 1 minus the probability x is at most 2n. And that's less than or equal to 1 over n. Okay, cool. Well, now we're going to use basically just the definition of a Poisson random variable. So let's just write this here. If y is Poisson theta and m is some positive integer, then the probability that y equals m, just by definition of a Poisson random variable, is going to be e to the negative theta times theta to the m over m factorial. That's just the definition of a Poisson random variable. So what's the probability x is at most 2n? Well, that's probability x is 0, plus probability x is 1, and so on. So I'm going to get 1 minus. The probability x is 0. Well, I just can just sub that into here. So that's going to be e to the minus n times n to the 0 over 0 factorial plus, and then the probability x is 2. That's going to be e to the minus n times n to the 1 over 1 factorial plus then e to the minus n times n squared over 2 factorial and so on all the way up to e to the minus n times n to the 2n over 2n factorial. And this is all at most 1 over n. And now this is essentially what we have here. You just basically rearrange this, which I've run out of space, so I'm not going to do. You factor out the e to the minus n from this huge bracket here, and you just rearrange, and you get this result up here. And that here proves our lemma.